Welcome to our last alkene video. In this video, I'll tell you about how alkenes react with chlorine water, bromine water, and then how they undergo reaction with ozone in what we call ozonization and then ozonolysis. So first, up there you have an alkene, and I've made sure that the alkene supplied is asymmetrical, so that we go straight to the point, because if the alkene is symmetrical, then there'll be no principles. Maconical's rule would not apply. But I want Maconical's rule to apply straight up, so that if you meet a case where there's symmetry, then you can easily survive it. So look at this one. Here's but one in, it's asymmetrical. Then that's chlorine water, HOCl. If HOCl were to be given charges now, would have OH or HO negative and then Cl positive. That's how we'd put the charges. HO negative, Cl positive. So that, according to Maconical, there was a version we stated where it said that we should give H to the carbon that already has more H. But I said we could also think about it as give the negative to the carbon with less H. So if you are giving negative to the carbon with less H, it means you'll be giving positive to the carbon with more H. So that in this case, our product will be drawn like this. This is our product. I've not added anything yet, so we add the positive part, which is the chlorine, to this first carbon, because just as H can be positive when we have it in compounds, that's how we take this chlorine to be equivalent to that, and then the OH being the negative part will stay here, OH. Once again, the OH is the functional group, the main guy here. You can see that it is inwards according to Maconical's rule. So the positive part in this case is our chlorine, while the negative is the OH. This compound you are looking at is said to be a chlorohydrin, and it is one of the halohydrins. So halohydrins are formed when alkanes react with hypohalous acids, chlorine water, bromine water. You get the halohydrins. So this is a halohydrin. Its IUPAC name is 1-chloro-butanol. 1-chloro-butanol. That's an example of the chlorohydrins or halohydrins. So this is how alkenes react with chlorine water. But what if this were Br? That would be bromine water. And that means that in place of a chlorohydrin, we would have gotten a bromohydrin. So in any case, when chlorine water, bromine water, and the others are to react, your halogen becomes the positive part of the addendum, while the OH is the negative. At this point, we'll move on to the big one, ozonolysis. Ozonolysis of alkenes. What does it involve? Let's look at it in words first. During ozonization and ozonolysis, you have an alkene combining with ozone. When this alkene combines with ozone, it first gives you an intermediate that we call a molozonide. Then, the molozonide, by what we call cycloaddition, or retro 1,3 cycloreversion or retro 1,3 cycloaddition, yeah. The molozonide is able to rearrange itself into what we call an ozonide. So ozonides are not formed immediately when alkenes combine with ozone. Instead, a molozonide is obtained first, and then we get an ozonide finally. This is the process of ozonization. Now, what happens to our ozonide? Our ozonide will be reacted with an oxygen acceptor, such as water or ethanoic acid, and that will occur in the presence or absence of zinc, so that the ozonide becomes degraded. It becomes split into two products, A and B. Now, what are A and B? If zinc is present during this second phase of the reaction, then A could be an alkanal, while B is also an alkanal. Or A is an alkanone, and B is also an alkanone. Or one of them is an alkanal, A or B, while the other one is an alkanone. So we are saying that in the presence of zinc, the products A and B can be two alkanals or two alkanones, or one alkanal and one alkanone. That's when zinc is present. But in the absence of zinc, so let me write no zinc. In the absence of zinc now, every alkanal that is supposed to have been formed will manifest as an alkanoic acid. So that instead of alkanal when zinc is present, what we get is alkanoic acid and alkanoic acid. But in a case where you are supposed to get alkanone and alkanone, you can get your alkanone irrespective of whether zinc is there or not. But see this last case where we would have gotten one alkanal, one alkanone. In the absence of zinc, the alkanal becomes an alkanoic acid while the alkanone remains an alkanone. So I am saying in effect that whether there is zinc or not, you can obtain an alkanone as one of the products or even the two products. Alkanones can be formed. But an alkanal product from ozonolysis is only possible when zinc is present. But if zinc is absent, then where you are supposed to get alkanoic acid, where you're supposed to get alkanal, you are going to get alkanoic acid instead. So this type of breakdown of an ozonide where zinc is present is referred to as reductive workup. We call it reductive workup. Then this other type where there is no zinc is called oxidative workup. So workup of an ozonide can be of two types: reductive workup, which occurs in the presence of zinc, and oxidative workup, which occurs in the absence of zinc. Those are the two types of workups that could occur to an ozonide, that could happen to an ozonide during this reaction, ozonolysis. So having tried to lay the foundation now, let's begin to draw structures and account for certain things that we said in that first part of the description. So let's say we have an alkene. Let's draw an alkene as R1C, R2, double bond C, then R3, and this is R4. Of course, this is an alkene. The double bond says so. When this alkene combines with ozone, it normally does so in the presence of tetrachloromethane. Now, the tetrachloromethane is a solvent for the alkene. So the alkene is dissolved in tetrachloromethane and then ozone is passed through it. When that happens, we get a product that looks like this: R1, C, R2, then this is C, R4, this is R3, then we have O, O, and O. This product we are looking at is called a molozonide. And we said when this molozonide undergoes a rearrangement, so let me just call it R there, we then get an ozonide. The ozonide will look like this: R1C, R2, then this is oxygen, and that is C. Then we have R3 and R4. Then down here, oxygen, and down there, oxygen. See this now. This is called an ozonide. The ozonide differs from the molozonide in that, you may look at it this way: in the molozonide, there is still a carbon-to-carbon bond. That is, the sigma component of the carbon-to-carbon double bond is still present. But in this case, it's not there. Nothing links the two carbons. In the alternative, you may think of it this way, that looking at the two carbons as being on a plane, in the molozonide, all three oxygens are on one side of the plane. But in an ozonide, what do you see? 2:1. They are distributed across both sides of the plane. So that is what we call an ozonide. Now the ozonide has been formed, which is the first line here. We've shown that in structure. But in the second line, we said to break down the ozonide, we need water. And there's that term I used to describe the water. I called it an oxygen acceptor. Why? Because this is what do you call it now? Ozonide. Let's say we have water here, H2O. With the approach of water, this ozonide splits like this. You see that splitting. Following this broken line, following this particular line, what do we have on this side now? We have R1C, R2. Permit me to remove this now. R2, beautiful. And then that C has an oxygen attached. You see it with a bond, and then there's half a bond there. So let's say double bond O. So both bonds come together to hold the oxygen, and something similar happens on that side. So that on that side we have R3 bonded to C, and then R4. Then again, this has O with half a bond, so double bond O. Now you see that there's one oxygen left. That oxygen left is accepted by this water to give us a third product, which is hydrogen peroxide. Now, the products of this breakdown of the ozonide, see them, 3. Hydrogen peroxide and these two guys. Now, for these two, imagine that I put H here and H there. That would be the simplest alkanal called methanal. But what if I put H here and that one is an alkyl group? That would still be an alkanal. But if I make the two of them alkyl groups, then this becomes an alkanone. So in this case, breaking down the ozonide has given us 2 products. And for these 2 products you are looking at, it's possible that they are both alkanones. Yes, they will remain as alkanones. It's possible that one of them is an alkanone, the other is an alkanal. Now, if any of them is an alkanal, this hydrogen peroxide, being an oxidizing agent, will oxidize that alkanal into acid. That's why we said that it's possible that you get acid in place of an alkanal. But what if I want the alkanal? I don't want acid. I want the alkanal to persist. That is where I now bring in zinc. So the work of zinc would be to reduce the hydrogen peroxide as soon as it is formed, so that if any alkanal occurs among these 2 products, the alkanal can stay, the alkanal can persist and not get oxidized by this guy. But if there's no zinc, then there cannot be alkanal, because hydrogen peroxide will oxidize any alkanal formed. So that's why we said here that when zinc is present, then it's possible that both products are alkanals and they will remain. It's possible that they are alkanones, and even if only one of them is an alkanal, it remains an alkanal. But if there's no zinc to take care of the hydrogen peroxide, then any alkanal you would have had as product becomes oxidized to the corresponding alkanoic acid. So let's draw a real example now, a real alkene, and see what it gives us on ozonization followed by ozonolysis. But you may pause the video for a while to go through the things I have said. Write whatever you wish to write before moving on to this next section. So in this next section, I'm going to draw an alkene, and we'll try to see what the products of its ozonolysis would be. Usually in the exam, when you are to be asked this, nobody will tell you about reductive or oxidative workup. You'd usually see everything in the equation. Imagine you had question 7 in an exam this way: H, C, and then C, C, C again, then this CH3, This H, and then double bond H, and H. Beautiful. So this is an alkene now. And then in front of the alkene here, we have an R, O3, then CCl4, then Zn, then H2O. This is obviously ozonization followed by reductive workup. Now, having said this, what happens when I start the reaction, or how do I get my products? I tell you, under exam conditions, you don't need to draw an ozonide. Just do it this simply. Take the alkene you have been given. Of course, it will have a double bond like this. Cut it along the double bond and you will see two halves. Let's draw the two halves here. This is H, C, H, H, then followed by what? C, H, and then double bond O. So see, from that half double bond, I gave the left side O. I will do the same to the right side. You know, on the right side, drawing from here, what I have first is CH3, which is this, followed by C, that has CH3 down, and then double bond, which is this, and I'll give it O. So it's as though we are saying, cut along the double bond, give the resulting left O, and give the resulting right O. Those will be your two products. And if you ask me to name these products, I will call this one ethanol. Why am I calling it ethanol now? Because this is CH3, which is an alkyl group. Then this is CHO. So RCHO, that's an alkanal. And this alkanal has how many carbons? 2 carbons. So that's ethanol. But on this side, I have 3 carbons. So I'm thinking prop. All the carbon to carbon bonds are single, so I'm thinking an. Then this is RCOR. That's an alkanone, so that's propanone. So I have ethanol and propanone. And will those be my final products? Yes, they will be my final products. The ethanol will persist. Why? There's zinc. So hydrogen peroxide will be powerless. But what if the zinc were not there? Just water. That would have been oxidative workup. And instead of reporting ethanol and propanone, I would have reported ethanoic acid and propanone, in that the ethanol would have been oxidized to ethanoic acid. So anytime you are given an alkene and they ask you, what do you get from its ozonolysis? Just cut along the double bond. Give the left oxygen, give the right oxygen. If it's by reductive workup, submit immediately, like submit those products like that. But if it's by oxidative workup, then check the products. If there's any alkanal in the products, report that as the corresponding alkanoic acid, bearing in mind that hydrogen peroxide would not allow that alkanal product stay. To close this, it's possible that you get a question where you are given the names of 2 carbonyl compounds like this. Maybe they say propanal and 2-methyl butanone, or 2-methyl 3-pentanone. Beautiful. See these 2 carbonyl compounds, propanal and 2-methyl 3-pentanone. And the question is this, they say, which alkene will undergo ozonolysis to give these 2 products? So that's like taking you back, because in the original question here, we gave you an alkene and requested the products. But in this case, they are giving you the products and requesting the alkene. And it will be very simple to do, because when we gave you the alkene and asked for the products, all you had to do was cut along the double bond, give the left oxygen and give the right oxygen. Then you had these 2 products. So if you have the products already and you want the alkene, you just do the reverse, which is remove the oxygens and join back whatever you had at first. It's simple. This is your alkene. Step 1, cut. Step 2, give oxygen. So you cut and you gave oxygen. So what would happen in the reverse? Instead of give oxygen, take oxygen, and then step 2, join. So let's draw these 2 guys first. Propanal is drawn like this. This is propanal. let's say double bond O there and H here. So this is propanol, easily drawn. And then the other one is 2-methyl-3-pentanone. We can draw 2-methyl-3-pentanone. First thing is to draw a 5-carbon chain like this. 1, 2, 3, 4, 5. That's pent. Then they said 3-pentanone, so my double bond O will be on carbon 3. Then 2-methyl means I'm going to put CH3 up there. So that's all. This is my 2-methyl-3-pentanone. But this 2-methyl-3-pentanone, I want to draw it in such a way that its oxygen can face this oxygen. So I'll do that here now. Let me bring the two compounds down here. The upper compound is drawn like this, CH3, then CH2, then CH and O. So this is the first compound. This is my propanol. Then for this one, I want to bend all of this down and bring that oxygen here. So that would be O double bond C. So that down here I have CH2, CH3. Alright, these ones have gone down there. Then on that side I have C with CH3 on top and then CH3. So all I have done here is to draw the two products that they gave me, looking for the alkene now. So see my first step. Step 1, remove the oxygens. Step 2, join. So to join means I'll do this 1 and then 2. So this compound we are looking at is our final product, and its name is, let's see, 1, 2, 3. So that's 3 in, hex 3 in. So we have 3 ethyl 2 methyl hex 3 in. So this is the IUPAC name of the alkene that would give propanol and 2-methyl-3-pentanone on ozonolysis. I didn't mention earlier, but let me mention now that ozonolysis is a very important way, or a very good way of determining the structure of an alkene. Yeah, that's its usefulness. It's used to determine structure. Unlike hydrogenation that can be used to determine degree of unsaturation, in the case of ozonolysis, its main importance is to determine the structure of an alkene, to know the position of the double bond in an alkene, because that's what determines the products that you get when the ozonide is split or when it undergoes ozonolysis like this. So we are done with alkenes, and it is my hope that you get the best out of this video. But remember, you need to give us a like, very, very important, because it keeps us going. And then also remember to share. Let your friends hear of this channel, let them see this video, and most importantly, remember to subscribe. Thanks for watching. I'll see us in our next video.